Alright, so let's start with the warm-up. So does this equation, matrix times x equals the 0 vector, have a non-trivial solution? We know it has solutions, we know it's consistent because it's a homogeneous equation. So we want to find out if it has non-trivial solutions. So what are we going to do? Pretty much the only thing we know how to do, right? We're going to row reduce. So I'm going to take this thing and row reduce. I'll leave the first row the same. I'll take the second row minus the first row. 0, 1, 0. I'll take the third row minus 2 times the first row. I'll get 0, 1, 0. I'll keep the first row the same, keep the second row the same. And now I'm going to take the third row minus the second row. This. Now at this point I should be able to tell whether there are non-trivial solutions. Are there non-trivial solutions? There certainly are, because I have free variables. What's my free variable here?
X3.
X3. Alright, so now I have an REF form so I can make those statements, find the actual solutions. I want to put it in reduced row echelon form. So I'm going to take the first row and subtract the second row. So I'll have this. From here I'll generate my linear system. It's going to be x1 plus x3 equals 0, x2 equals 0. Where do these zeros come from?
0 vector.
0 vector, right? I didn't actually write the augmented matrix because I didn't need to because it's a homogeneous system, but that is what's on the right-hand side here. So I have my linear system. I'm going to put this in parametric form just because it's easier to work with. So I'm just going to write x1 is equal to negative x3, x2 is equal to 0, x3 is equal to, well, x3 is the free variable. So my solution vector, which is just a vector of the individual solutions here, it's going to look like negative x3, 0, and x3. I'll factor out that parameter and write it like this. If you want to call it S, you're more than welcome to. That looks like a good solution. All right, any questions about that solution? Once again, it's a lot of discussion that goes with that solution process. That's the important stuff. All right, any questions? All right, so if there's no questions, we'll move on to section 1.7, linear dependence. All right, so hopefully you went through the reading. I really like the way they started this section and kind of frame it in terms of what we've been doing. In the last section, we talked about homogeneous equations. These equations, AX equals 0, and that should be the 0 vector here. And we were trying to find non-trivial solutions. But we can think about that also in terms of its vector equation. That's the same thing as saying AX equals 0 is saying that x1 plus some vector, which is the column of A, plus x2 times the next column, so on and so forth, equals 0. That's really the same statement. And so if we take our last question here, are there non-trivial solutions, and frame it in terms of the vector equation, we can see that asking if AX equals 0 has non-trivial solutions is really the same thing as asking, is there a linear combination where that x1, x2, x3 are not all 0 that's going to get me to 0? It's the same thing as asking if there is a linear combination, not all zeros, where I can take a linear combination of those vectors to get to 0. I mean, clearly we can see that x1 equals 0, x2 equals 0, x3 equals 0 will work here. The question is, are there non-zero ones? So the idea is if there are only that solution, if it's only x1 equals 0, x2 equals 0, x3 equals 0, then we're going to say that this set of vectors here, we'll say the set of vectors is linearly independent. So a set of vectors is linearly independent if and only if the only linear combination that gets 0 is 0, 0, 0. That's really our definition of linear independence. So you can see it's really just characterizing the set when we don't have non-trivial solutions, when the only solution is trivial. So saying the set of columns, or the set of vectors is linearly independent is saying the same thing as there's only the trivial solution. And if there are linear, if there are x1, x2, x3 not all 0, or I can find a linear combination that gives me 0, and there are non-trivial solutions. All right, any questions about that? Just the definition from the reading. All right, so from the reading, that's really what I want to get is that definition. Linear, independent, and dependent. The next question is how are we able to determine if a set of vectors is linearly independent or dependent? So now we have the definition. How do we take a set and determine whether this is true? Before we go too far into that, let's have a little clicker quiz. So this one's going to be a non-graded, just clicker kind of questions. So basically A is linearly independent, B is linearly dependent, and we're going to go through and say what goes in the blank for number 1. So this set of vectors, v1, v2, ... vp, is said to be which? Independent or dependent? If there exists some weights, not all 0, such that linear combination is true. Independent or dependent? As soon as you show it, it tends to swing one way or the other, right? Okay. All right, so this is B. This is linearly dependent. So we can find this. We can find the x1, x2 that are not all 0 that give us linear combination. So there are non-trivial solutions of this thing. So that's the definition of linearly dependent. So let's stop that one. Let's go to the next one. So number 2. And once again, as tends to be the case in linear algebra, we're really just trying to find 18 different obnoxious ways to say the same thing, right? But it's important to understand the verbiage that goes back and forth between these statements. So let's take a look, see what we did here. Okay, so strong consensus for A, absolutely. So here we're just saying that when does this vector equation have only the trivial solution? It's saying that only x1 equals 0, x2 equals 0, xp equals 0 will give me that linear combination. All right, so that one means that they are linearly independent. So once again, A is independent, B is dependent. So we'll stop this one, and we'll start the next one. Okay, so once again, a strong vote for A. A is correct here. So once again, the vector equation and the matrix equation are essentially the same. So we have linearly independence when there's only that trivial solution. And it's only values of 0 that make that linear combination equal to 0. And then lastly, here are 3 vectors. Are they linearly independent or linearly dependent? Quick answers. How do you tell this one? There's work to be done here. So how do we start this problem? What are we thinking about here, these vectors? Absolutely. We're pretty much looking at the statement above here. So okay, if that thing has a trivial solution, and that's the only solution, then it's going to be linearly independent. So let's just take these vectors and write them as a matrix, thinking about AX equals 0, and see if we can find the solutions. Right? If the solutions are only X equals 0, then it's going to be independent. If it's not, it'll be dependent. So we go ahead and reduce this thing. Let's see what we got here for totals here. Pretty mixed. So now we're going to row reduce this thing. I'll leave the first row the same. Leave the second row the same. I'll take the third row minus the first row. I'll get 0, minus 2, minus 3, minus a negative 1. That should be minus 2. Now I'm going to take the third row plus 2 times the second row to get this thing. Now I'm in REF form. So what do I know about the solutions to this homogeneous equation? Is there one solution or are there infinitely many solutions? Infinitely many because I have that free variable. X3 is a free variable. So if there are infinitely many solutions, are those vectors independent or dependent? Dependent. Right, it's independent only when there's the trivial solution. It's dependent when there are infinitely many solutions here. That one's going to be A. I'm sorry, D. B. Dependent. Okay, any questions about those? Okay. So now we have the big running expressions, right? We have so many different ways to represent these linear systems that any kind of theorem, any kind of statement we have about these is going to trickle down to about 8 different expressions. Let's go through them real quick here. A set of vectors in Rn is linearly independent if, right, then we have our definition. The vector equation, this thing has only the trivial solution. I guess our definition would be that there exists some x1, x2, xp, the only x1, x2, ... xp, such that the linear combination gives 0 are the 0 values. So then we have the vector equation, this thing only has a trivial solution. Or the matrix equation has only the trivial solution. And then we have a last statement here. None of the vectors can be expressed as a linear combination of the other vectors. All right, so what does that last statement really mean here? None of the vectors can be expressed as a linear combination of the other vectors. So how is no free variables related to that last expression, though?
It would be in the span.
So it wouldn't be in the span of which two vectors?
The
other
vectors.
The other vectors, absolutely. So, if they're linearly independent, then this one is not in the span of these two vectors. That's another way to restate that. Absolutely. So none of the vectors is in the span of the other vectors. So let's see why that kind of makes sense here. So let's take the opposite case here. Let's say that we can express so let's assume it was dependent. So we have our vectors. So here's x1, v1 plus x2, v2 plus ... plus xp, vp equal to the 0 vector. And all the v's are vectors here. So now, if this thing is linearly independent, then for this thing to be true, x1 has to be 0, x2, all they have to be 0. If we're in the other case, and maybe one of these is not 0, we could have number values and find some linear combination to get us to 0. That's the other case where it's dependent. But if that's a true statement, Right? If there's 2v1 plus 4v2 plus this thing, right? If we can have some values that actually the sum gives us to 0, we'd have this equation here. Then I could just grab one of them, like this one, and move it to the other side. I mean, it's just 2vp, whatever that number is. So I could just rewrite that as this thing. Like that. Or that x, negative xp is just some number. Now it's negative 2 because I moved it over. But if it's just a number, I could also divide by it. Right? So if I divided this whole equation by negative xp, I'd have x1 over xp, it's v1, plus x2 over a negative xp, v2 plus dot 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 is equal to vp. Now what is this really saying? These are just number values. So it's saying there's a linear combination, some number times this one plus some number times this one, dot 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 dot, that is equal to this other vector. So it's saying vp is a linear combination of these two. It's saying vp isn't something new. It's just adding up the other ones. We haven't really added any value by including vp in this set here. Any questions about that? Okay, so this isn't really a proof of the statement. This is just kind of a, yeah, this kind of makes sense because if we do this, once again, linear algebra is kind of an introduction to a proof course. So I felt compelled to write out the full proof and just kind of talk our way through it. I won't ask you to make this proof, but I want to point out a couple different characteristics of the proof that are important in a proof of this kind. So first you have to start off with a formal statement here of the thing you're trying to prove. So here we have theorem 7 from the book. It says the set of vectors, v1, blah, 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 is linearly dependent if and only if. Right, so there's our IFF statement, or the double-sided arrow that we're using. If and only if at least one of the vectors is a linear combination of the others. So the first thing about doing a proof like this is when they have an if and only if statement, that means you have to do two proofs. You have to show that if this is true, then this is true. But you also have to prove the other way around, that if this is true, then this is true. Because an if and only if is a pretty powerful statement. There's lots of statements that say that if this is true, then this is true, but it doesn't work the other way. If and only if means it works both ways. But that means you have to prove both directions as well. Okay? So here, I have my little arrows say, first I'm going to prove it one direction, and then later I'm going to prove it in the other direction. Okay? So I start out with what I know. It says that I'm saying that if this thing is linearly independent, then at least one of the vectors is a linear combination of the others. So I have my set of vectors I call F. I know that it's linearly dependent. I got to use the definition of linear dependence. So if it's linear dependent, then there exists, this is another fancy symbol here, right? That upside down A means for any, and this backwards E thing means there exists. So there exists, somewhere out there, there exists some x1 dot xp, not all of whom are 0. Many of them could be 0, but there's at least one of them there that's not 0, such that this thing is true. That's the definition of linear dependence. And then I have my WALG here. What does WALG mean? You know what WALG means? It means without loss of generality. So it says without loss of generality, I'm going to say let this one not be equal to 0. Now what I'm saying here is that I don't really know if this one's not equal to 0. I know one of them is not equal to 0, but I don't know if it's this one. I also don't really care which one it is. Maybe it's W2, V2. I don't care. One of them is not equal to 0. Choose that one. So without losing the generality of the problem, I'm going to pick one and say, yeah, this is the one. Okay? So if that one's not equal to 0, then I can move that one to the other side like we did kind of heuristically, divide through, and I can show that this is a linear combination. Okay? So that's more of the formal statement of the proof. So you can see that stuff we did up ahead, that's how you might think about the proof. Yeah, this makes sense because if I move one over and I subtract, divide it, and yeah, I have a linear combination. So you do that kind of side work to think about how you might attack a proof, but then you have to do the formal write-up. So once again, the important pieces are that we have one direction where we're saying if this is true, then this is true. We've gone through and used the definition to show that. And now we would have to do it the other way. We have to say that if at least one is a linear combination, then that set of vectors is linearly dependent. So that's just using the definitions backwards. Oops. So now we say if, without loss of generality, one of them is a linear combination of the others. Well, what does it mean to be a linear combination of the others? It means exactly this thing. Right? Well, if not all the x is 0. Well, then I just do the addition backwards to write it like this, and then that's the definition of linear dependence. So it's there's not a whole lot of moving parts here. It's really two definitions that we use them. We use the first definition and the second. And way back we use the second and then the first. Okay, but it's the structure that's kind of important to see once or twice. All right, any questions about this proof? All right, congratulations, you survived the proof. Hooray. Everybody's favorite part of the class, I'm sure. All right. So now we're got through the proof that says that stuff. But why? The biggest question here is why. Why are we concerned with this idea of linear independence and dependence? So one way to talk about that is to look at this case here. We've talked about this case before where we have this vector and this other vector. We've talked about a linear combination. We've talked about the span of these two vectors. What is the span of these two vectors? Describe the span for me.
X and Y point.
What's that?
Any X and Y point.
Any X and Y point. Any point in this plane. We could say that the span of this thing, span of V1, V2, is equal to all of R2. R2 is the set of all two-dimensional vectors, or the set of all points in the plane. The way we kind of think about that. So in other words, is there a linear combination? Is there a linear combination of V1 and V2 that equal 3, 9? There is, right? I can get to any other point in the plane with a linear combination of these two things. So what about this new set of vectors? Negative 1, 1, 2, 1, and 3, 9. What's the span of those three vectors? Have I changed the span? It's still just R2. I haven't really added any points. There aren't any new points I can get to that I couldn't have gotten to before. I haven't changed the span. So it's like, boy, I don't really need all three of these. Right? If you want to give me directions to some random point, I can just really use these two directions to get there. I don't need to add this third direction. I have an extra one here. It's kind of redundant. It's redundant because I don't need it. There's a linear combination of these two things that will get me to this. So this is an extra piece. This new set is not a linearly independent set. If it was linearly independent, that means I know they're all useful. If I want to get somewhere, I really need to use both of these things to get to some random spot. But if I add this other piece, it's kind of like an extra piece. So what we want to do is we want to find enough vectors so we can describe all of R2, but we don't want to have any extra ones. So we need just the right number of these vectors. We need enough so that we can get everywhere, so the span is all of R2. We also don't want to have any extra ones, so we want this set to be linearly independent. So that's one of the big ideas of linear independence, is to find just the right number of vectors to describe this whole space here. So moving on to 3 dimensions, we have this thing. Now, can I get to all the points with these two vectors? Can I get to the point 3, 4, 6 using those two vectors? I can't. So can I get to all the points in R3 using these two vectors? I can't. So these two vectors do not span R3. Well, that makes sense. I only got 2 of them, right? Let's add a third one. Let's add 2, 4, 0. Now I have 3 vectors. Do these 3 vectors span R3? They don't, right? I mean, you can kind of see that they don't because there's no way I can get some value in that third component. In other cases, it might be more complicated. And so how do we tell if these things are going to span the space? We check to see if they're independent or not. It turns out for me to span R3, I need 3 vectors. But not just any 3 vectors, I need 3 linearly independent vectors. So that's one way we're going to use this also. All right, any questions about that? We're going to talk a lot more about that when we introduce what a basis is. Question? All right, so now we have a little idea of maybe how we, or why we might want to determine whether a set is independent or dependent. Next question is, how do we do that? How do we tell if a set is linearly independent or dependent? Well, we've already done that one way. We've talked about the relationship between this statement and also a vector equation and a matrix equation. So we know that in general, if I have these, and I want to tell if they're linearly independent or dependent, I want to see if there's some linear combination of these things that equals 0. Or I might want to say I could just take those vectors, put them in the columns of a matrix, and say, are there non-trivial solutions to this homogeneous equation? So if I want to tell if this set is linearly independent, I can just throw it into a homogeneous equation. Now I have this thing. I'm just going to take this. I'm going to do my row reduction on this. I'm going to have a couple different possibilities for outcomes. One outcome would be this thing. A bunch of zeros up there and down there. If I get that as my row reduced matrix, what would that tell me about whether these are linearly independent or dependent? Why? So that means it's independent here. So this will be independent because there's only the trivial solution. Right? It's easy to get these backwards. Right? So we're going through a whole bunch of these, but at the end of the day, it's easy to get them backwards. Right? So it's linearly independent if there's only the trivial solution. So in this case, I'd say, oh yeah, x1 is 0, x2 is 0, x3 is 0, x4 is 0. Only the trivial solution. Therefore, these would be independent. Think about it in terms of that spanning idea. Right? We're going to need each one of these, if this is independent, to actually define the space. Right? They're all pointing in the independent direction you could think of. None of them are pointing in the same direction. All right, so then if I had a case where it was like this, and who knows, you could have numbers here if you want, 2, 4, 6. In that case, there would be a free variable. So there would be infinitely many solutions. So there would definitely be non-trivial solutions. In this case, the set would be dependent. One of them is redundant. One of them is just a linear combination of the others. So that's kind of the formal way to show it. We can use that process for any set of vectors. We can throw them in that matrix. We can do the row reduction. And we just have to make the right decision when we're done. But a lot of times we don't want to go through all those steps. We want to take shortcuts pretty much whenever we can, right? So there's some shortcuts that we can take to determining whether a set of vectors is linearly independent or dependent. So the first one is, if 0 is in the set, then the set is automatically linearly dependent. Now that's a 0 vector, of course, not a 0 like in one of the components. But if the 0 vector is in the set, then it's automatically linear dependent. No analysis needed. So the question is why? Why is that? Why don't you take a second and chat with your neighbor and see if you can come up with a reason for why that makes sense. Feel free to write some stuff down here. Think about the definitions. What is the definition of linearly dependent? What would that mean? Write something down and see if you can come up with Y'all got reasons here?
Yeah.
All right, what do you got for a reason for me?
It's going to cause one of the variables to be a free variable. Oh wait, that's independent, isn't it? I think one will be a free variable.
Sure, absolutely.
So infinitely many solutions.
Right, we could write that in there and there'd be some sort of 0 column. No matter what the row operations, we're still going to have a 0 column, so that would be a free variable, absolutely. That's a perfectly good justification why this makes sense. I heard another one over here. What was yours?
The 0 vector doesn't add anything to the space.
Absolutely. So we're talking about those linear combinations to span the space. 0 vector is not going to help us get anywhere, right? So that's another way you can think about it. Any other ideas? Any other justifications that are different? Here's another one. If there's linearly dependent, if and only if I can find some non-zero x1, x2, x3, we'll just stop it at 3 for argument's sake here. If this one's 0, 0, 0, I can find a non-zero x1, x2, x3 to make that work. 0, 50, and 0. Right? That will add those up to 0. So that's a non-zero x1, x2, x3, where the linear combination gets me to the 0 vector. That's another way you can justify that. Okay, all three are excellent, though. Any questions about that one? All right, 2. If the set has only 2 vectors, there's a shortcut. Find out whether they're an independent set or a dependent set. That's a shortcut if there's only 2 vectors in our set.
See if there's a scalar.
Absolutely. Seeing if there's a scalar. If they can multiply one to get the other, then they have to be linearly dependent. And they're only linearly independent if they're not multiples of each other. Because really what you're saying here is, well, remember, for this thing to be independent, they can't be linear combinations of each other. But there's only 2. So you're saying, is this one a linear combination of this one? Well, a linear combination of one vector is just a scaling of the vector. Any other vectors add to it. Okay, so if this one is a linear combination of this one, it just says that there's some number times this one that will get me to here. Right, so there's only 2 vectors. All we're really doing is see is they're multiples. Now, graphically, we can see that. Here's one vector in 2 dimensions. Right? And I would say, is that one linearly independent? Sure, right? That linear combination will give me more stuff. Is this one linearly independent? I'm not really adding any dimension here. I'm not getting any new vectors. Any vector I could have gotten to by multiplying this by some number, I can also get to by multiplying this by some number. So those 2 vectors are not independent. They're just multiples of each other. Okay, so what about these ones? Independent or dependent? They're just multiples of each other, which means that they're dependent. Absolutely. So these are dependent. What about the next one? Dependent. Right. But that's a little trickier, right? It's not that nice integer multiplier. Right? So you might have to do a little work to see if they're multiples of each other. Right? What do? Well, just take the quotient of these things. 4.5 divided by 2. Right? If they're multiples, then that would be the multiple. That's the thing you would multiply to get from one to the next. So is that the same as 9 divided by 4? Right? And it is. Okay. So if you want to find out if they are multiples and you have a bunch of weird numbers, right, just pick one and find out what times this gets me to this and see if it works for all the rest of them. That's all you're really doing. All right, questions about that? So these are the shortcuts that help us so we don't have to necessarily throw everything into a matrix and row reduce. What about the last one? If there are too many vectors in the set. Too many vectors in the set. What does this one mean?
Only 2 vectors per R2.
Absolutely. So in this case specifically, we're in R2. We've talked a whole bunch of times now where any linear combination of these 2, I should be able to get to anywhere in the whole space. It only takes me 2 linearly independent vectors to get to anywhere in R2. It will span R2. So if I have 3 of them, one of them has to be redundant. All right, if I can get to anywhere in the space as a linear combination of these 2, that means I can get to here. And so that one means that one has to be a linear combination of the other 2. Okay. Now, it turns out that I need 2 linearly independent vectors to span R2. I need 3 linearly independent vectors to span R3. How many do I need for R4? 4. All right, so on and so forth. So in other words, if I have this set here, 1, 2, 3, 0, 0, 1, 1, 2, 9er, 0, 1, 1. Linearly independent or dependent?
Linear independent. Dependent?
Dependent. Dependent, because one of these has to depend on the other ones. One of these is a linear combination of the other ones. I have too many here. I only need 3 of these to span all of R3. So if I know that I only need 3 of them, one of them has to be redundant. I don't know if it's this one. Maybe I need this one. Right? But one of them is redundant for sure. Okay? So I can just look at that set without doing any calculations, without throwing it into a matrix and doing a reduction. I'll just know that. Now there's another way I can kind of justify that as well. That's by looking at the matrix. Right? If I look at that matrix, like I was just going to say, well, I didn't recognize that the dimensions worked, so I'm just going to go through and by force do the row reduction. Now think of the possible outcomes for this. If I'm doing that row reduction, I could get a 1 there. I might be able to get a 1 here. I might be able to get a 1 here. Right? But then I have some numbers here. I'm going to have a free variable. If I have a free variable, I have infinitely many solutions. If there's a free variable, this is a dependent set. Right? So even just by thinking about how the row reduction will end up, I'm going to be in trouble. Because if I count my columns, 1, 2, 3, 4 columns, that means I have 4 variables. The basic variables are going to have pivot positions. But I can only have 3 of them. I can't have a 4th one. So one of them has to be a free variable. Questions about that? That's really that next step here, is we can just look at the dimensions of some matrix and determine that right away. So here I have an M by N matrix. And the statement is, if M is less than N, the columns must be linearly dependent. Like justification is what we just talked about. Really, it's those pivot positions, those pivot columns, that are marking my basic variables. It's the columns that don't have pivot positions. Those are my free variables. But all it takes is one free variable to say that this thing is linearly dependent. And I can only have a pivot position for every row. So if M is less than N, the columns must be linearly dependent. This means the set of vectors, or a set of columns, is linearly dependent. Dependent. Which is the same thing as saying that AX equals 0 has what kind of solutions? Just trivial or non-trivial? So if M is less than N, we have a linearly dependent column vectors. That tells us that AX equals 0 has what kind of solutions? So, clicker quiz. A says it only has trivial solution. And B says it has non-trivial solution. Can't tell if we're tired or not sure. Alright, so now the columns are dependent. We're pretty happy with that. Pretty happy. Getting happier. So B, non-trivial solutions. Remember, it's valuable to have a lot of different ways to think about the same concept. This also implies that we have free variables, that AX has free variables. This also implies that there are columns without pivot positions. In this case, we're really not trying just to be obnoxious. We actually have other reasons to write all of these things over. Because the idea is that these are all kind of useful here. Right? If we can see that it has no pivot positions, then we can jump right away to saying that it does have non-trivial solutions. And that's a nice visual jump to make. Okay, so some of these are telling us the nice things we know once we determine that it's dependent, and some of these are telling us nice ways to see that they are dependent. So now if we have this thing and we can see that there are columns without pivot positions, we can know right away that those columns are dependent. Okay, what about the other case? What if m is greater than n? What does that mean? I got my hook here, trying to bait you. I got him, right? It'll be independent, right? These two are independent. So you might say, well, if m is greater than n, they should be independent. But I could also have this one. Right? Same case, m is greater than n, but now these two columns are dependent. Easy enough to see because this is just a multiple of this. Okay? I know it's mean, right? Like, come on. Nah, wrong. But we have to be careful of that because it's an obvious assumption to try and make. Right? It's a thing that we all try to do. Yeah, that makes sense. The other way it must be independent, but it's not true here. Okay, so it's important to think about that example here. Okay. Okay. So let's do a little bit of practice here. Quick clicker quiz, and then this should about end this up here. So, independent or dependent. We'll start off with number 1 here. Independent or dependent. This set of vectors, independent or dependent. All right, most saying dependent. So if it's dependent, why is it dependent? Someone justify it. Yep. So now we're looking at rows here, right? So if you're looking at rows, that's a very useful way to think about it. But because we haven't really formalized that as a reason, like there is a theorem that says that these rows are multiple, then we're good. We have to take it to the next level then. What does that mean that these two rows are multiples of each other? We know that if columns are multiples, then right away those columns are dependent. But how can we go from rows being multiples to dependence as well? What's that? Yeah, then we'll have a free variable, absolutely. Yeah, so that's the next step, absolutely. Anybody else with another justification for this one?
Zero vectors in the set.
Zero vectors in the set, right? If there's a zero vector in the set, automatically dependent right away. Okay. What was yours?
Scalar. Just multiply the first one by 0.
Sure, that's another way to think of it, right? That will work for any time the zeros in the set, absolutely. Great. All right, we'll stop that one. We'll do the next one real quick. Independent or dependent, this set of vectors. kind of mixed here. Right? Maybe we're doing work here. Maybe we're trying to grab this thing and try to put it in that matrix and try to row reduce. But in this case, I don't need to. Right? This is the dimensional analysis here. I have three-dimensional vectors. I know that if I have three of those things, they should span all of R3. If I have the right three vectors, I should be able to any other vector in R3. Well, I have four of them here. So automatically, one of these has to be redundant. Has to be. So this one is dependent. So it's dependent because I have too many three-dimensional vectors. So this one is dependent. This one is dependent. Let's stop that one. Start the last one. Whoops. And the last one, independent or dependent? Independent. Independent because they're not multiples of each other. Right? If we just have two of them, the best way to test is to say, are they multiples of each other? They are clearly not multiples of each other, so they are independent. So those clicker questions are not just for me. Right? They're good for me to see how we're following along with the lesson. If we have questions, if I need to spend more time. But they're also good for you. Right? If you see the majority of people getting them right and you're on the wrong end of that, come see me. Right? We'll talk about it after class or in office hours and just work through those issues now before they get worse, before they lead into other problems. So office hours are right now, and I always look forward to seeing people in office hours.